Okay, good morning or good afternoon, 12D. In fact, maybe looking at the statistics, good evening is a more appropriate salutation. This video this week is all about Young's modulus, and it's in preparation for an assessed practical that we will do next week. Now, having learnt in the past few lessons about spring constants and Hooke's law, we now need to learn about Young's modulus for the main reason that Hooke's law actually isn't particularly useful. In today's video, you're going to compare the flow of current in a wire and the extension of a wire under force. Recall the equations for the spring constants of springs in series and parallel. And you're also going to consider the limitations of using the spring constant and discover Thomas Young's neat solution to the problem. So I want to start by making a simple analogy, and that is to the flow of current through a piece of wire. Now, when we try to pass current through a piece of wire, the wire's resistance to the passage of electrons, R, depends on three things: length of the wire, cross-sectional area of the wire, and the material property of the wire, that is resistivity, ignoring temperature for now. So I'm going to pause quickly and ask you if you can remember the equation that links these three properties. Okay, so hopefully you remembered that the equation that links these properties is, of course, resistance equals resistivity times length times cross-sectional area. That was just a brief revision because it's useful. The analogy is looking at the piece of wire when we try to stretch it and the wire's resistance to actually stretching. And the analogy holds because the resistance to being stretched of a piece of wire depends on the length of the wire, the cross-sectional area of the wire, and also the property of the wire that we call Young's modulus, which is what this video is all about. Now, we can see the effect of changing length and cross-sectional area on the spring constants of springs in series and parallel. So I'm going to start by outlining those. If we start with springs in series, we can see the effect of length on the amount of deformation. So here I have a basic setup with one spring with a spring constant K and a mass applied to it. And we know that the total spring constant of this setup is equal to the spring constant of that spring. If I now take two springs and put them in series, so I've got two springs with the same spring constant in series with a mass applied to them, you should know from this week that these 1 over the spring constant will actually be equal to 1 over the spring constant of the first spring plus 1 over the spring constant of the second spring, which simple math tells us is 2 over that spring constant, which we can rearrange to see that the spring constant in total is therefore half the spring constant of one of those springs. Note that this is exactly the opposite to what happens to resistors in series. So this actually looks like the equation for resistors in parallel, but we're talking about springs in series. It's important you don't get that confused. Now, I have a mass here and it's applied to the spring. If I were to double the amount of mass applied to this spring, you know that I would expect to see double the extension because of the direct proportionality. But for this setup here, if I were to double the mass, please tell me what you think would happen to the extension. Okay, so because the spring constant has halved, this setup is therefore less stiff, which means if I double the mass, I would expect to actually get quadruple the extension, or 2 times the amount of extension I expected when I doubled it over on this side. Now, if we look at pieces of wire of different lengths, just so we can see the analogy carry through, if I start with a particular length, when I apply mass, I get a change in length. But if I start with a wire of double the length, when I apply the same force, I would expect to see double the extension. That's because there is more material there to deform, so I will get a great amount of deformation. Now let's talk about springs in parallel. Again, from this week, you know with this very simple setup, the total spring constant of this setup is just the spring constant of this spring. And what you will hopefully remember is that for this second setup here, where the springs are in parallel, the total spring constant is just equal to the spring constants of each spring added together. So in other words, in this setup, 2 times the spring constant of the spring. So in other words, in this case, the arrangement has got stiffer. So whereas here, when I double the mass, I get double the extension, I'd like you to think about it again. If I double the mass in this arrangement, what would I expect to happen to the extension? Okay, so if I double the mass in this arrangement here, because I've got 2 lots of the spring constant, or I've got twice as stiff an arrangement, I would expect the extension to half. Again, I can look at this for wire of different thicknesses. So I start with a wire of a particular thickness and it has a length L. I apply a force and I get a change in length delta L. If I take a wire of twice the thickness, so twice the amount of material available to resist the deformation, when I apply the force I would get half the amount of extension. So for the same force I'm seeing half the amount of extension, the reason being that there is more material available to resist the deformation. Okay. So here I have a force extension curve, and I'd like to know what you think this force extension curve is showing. So I have got various lines of various different gradients, and I'd like you to vote now on what you think this graph shows. The answer is that this graph could actually show very many things. We can see stiffness or spring constant increasing from line to line. But is that because the thickness of the material is increasing? Is it because I'm testing wires of shorter and shorter lengths? Or is it because I'm even testing different materials? And if I am testing different materials, does this really show me anything? Am I able to compare those materials? In case you're curious, what it actually shows is various different materials. But without extra information, I have no way of knowing if this graph allows me to compare these materials. This is the problem with Hooke's law. Hooke's law tells us how much a spring or a material stretches for a particular force. So for a particular wire or a particular spring, it will tell me stiffness, but it doesn't tell me the length or the cross-sectional area of that spring or stiffness. So when it comes to trying to compare different materials or different springs, in order to use Hooke's law, I need them to have identical length and identical cross-sectional area every time. Because if they don't, then I don't know how much a different shape of that material is going to deform. Now, this is a problem, but luckily a scientist called Thomas Young came up with a solution. Thomas Young thought, we need a property that can compare the elastic deformation of different materials. It must take into account cross-sectional area and original length. What to do? What to do? He thought about it for quite a while, and he had a very bright idea, and he decided to split this problem into two counts. So there's the one of the effect of area and the one of the effect of length. Let's start with area. So he came up with a property, stress, signified by this Greek letter here, sigma. He knew that the greater the amount of material there was to resist the force, the greater it would extend. So he needed to know, for a particular material, how much force it could resist per unit area of the material. And he needed a way to take this into account. His solution was to make force proportional to original area. I need to point out that that should say area, not length. And he came up with this property stress, which he said was equal to force divided by cross-sectional area. So I now have force divided by cross-sectional area. I'm taking into account the area. Note that stress is measured in newtons per metre squared because I have force in newtons and area in metres squared. And actually newtons per metre squared are more generally called or described using pascals, PA, which is an SI unit of pressure. Newtons per metre squared and pascals are interchangeable, but it is preferable to use pascals instead of newtons per metre squared. Now, the second part of the problem that needed to be taken into account was the effect of length, the fact that greater length gave rise to greater deformation. And he came up with a property called strain, which he labelled epsilon, curly E. And again, this was because he knew that the longer the material was, the more it would extend. And so he needed to know how much extension we got per unit length of the material we were testing. So he made extension proportional to original length. He said that strain is equal to extension divided by original length. Another note on units here, strain actually is a unitless property. That's because we're dividing metres by metres. Occasionally you will see this times by 100 and strain given as a percentage, but in terms of SI units, strain is given as a unitless property. Now, the reason Young's idea was such a great one was it meant that different materials could be compared, and we didn't need them to be the same cross-sectional area and length in order to plot them on a curve and compare them. So here I have, instead of a force extension curve, a stress strain curve. And you can see that I get kind of similar shapes. I get this area of direct proportionality, and then I get things happening to the curve, which we will discuss in the weeks to come. And Young decided to name this directly proportional part of the curve here Young's modulus, which is designated E. Young's modulus, which is measured in pascals, because stress in pascals divided by strain with no units will give me the units of pascals. So this is a typical stress-strain curve. It shows various materials. They might have had different cross-sectional areas and lengths, but it doesn't matter because I am now just comparing the properties of the material, not the property of the object. So just to check you've been listening, which of these materials, A, B, C or D, has the highest Young's modulus? The answer, of course, is A, that has the steepest Young's modulus, because Young's modulus is the gradient of this line. So the steeper the gradient, the steeper the Young's modulus. Now I'm conscious that I'm running over the amount of time that I said each video would last, but I've still got a little bit of information I want to give to you. This slide here has the key pieces of information you need to know about Young's modulus. So E, or Young's modulus in pascals, is equal to stress, newtons per meter squared, or pascals divided by strain. And if we plug in the equations for stress and strain, we find that Young's modulus is force times original length divided by area times extension. Although, to be honest, all you're going to need to be able to do is calculate the gradient of the straight line on a stress-strain curve. That gives you the Young's modulus. Young's modulus is a measure of the force per unit area that is needed to stretch, sometimes compress, but not at A level, a material sample. I just want to finish by comparing Hooke's spring constant and Young's modulus. We've got Hooke and spring here. Now, Hooke's spring constant is K, and it's equal to force divided by length. It's measured in newtons per meter, and it is a property of an object, so it doesn't tell us anything about the effect of cross-sectional area and length, and it really is object-specific, making it not really that useful. On the flip side, Young's modulus, E, is equal to stress divided by strain. It's the gradient of a stress-strain curve, where stress is equal to force divided by area, and strain is equal to extension divided by the original length. And it's measured in newtons per meter squared, or pascals. Those two units are interchangeable, and it's a property of a material. So it really is incredibly useful. In fact, you could go away now and you could look up on the internet for all sorts of different materials what their Young's modulus is. And it's this property that engineers use throughout their life.